Thanks everyone for hanging in here till almost the end of the day. Great to see everybody. So I'm going to talk a little bit about what is actually quite a large collaborative project. I'm just, sort of the face of it, but we have a lot of graduate students working on this, and we're working primarily with end users of the South Florida Water Management District and Everglades National Park. So the relevance to this work, we're talking about coastal wetlands here in the Everglades. There's become, I think, probably a much greater awareness of the ecosystem services that coastal Everglades wetlands provide us, not only in South Florida, but in the state of Florida. And so I've just highlighted a couple of those here, one being buffering storm surge associated with extreme events, reducing erosion and protecting water supplies. Much of the drinking water in Miami-Dade County comes from the underlying aquifer, which is rehydrated through the Everglades. And then, of course, a big focus of the work that comes out of Florida Sea Grant, which is understanding the economic impacts of our tourism industry, as well as the resources that our coastlines provide to us. So this is a quick schematic of the Florida watershed that leads into the Everglades. So on the left hand here, you see sort of a schematic of the pre-drainage Everglades wetlands, water overflowing through through Kissimmee River Basin and into Everglades National Park, delivering quite a bit of fresh water through those coastal wetlands. With freshwater diversion, a lot of that coming out of Lake Okeechobee from the west and east sides, and an extensive drainage system through our urban area, we have a lot less fresh water moving through Everglades National Park and South Florida in general. And these yellow arrows here just are indicating the influence of saltwater intrusion as fresh water is diverted from the southern part of our state. And then this is sort of the anticipated outcome of a fully implemented comprehensive Everglades restoration program, where we have much more fresh water coming down through Everglades National Park in South Florida and having the effect of reducing the impact of saltwater intrusion into those wetlands. So our study was motivated by some work that was done in Everglades National Park by Hal Wanless, and he had looked at some aerial imagery and had noted a large loss of formerly freshwater peat marshes down at the end of Everglades National Park. This is the Cape Sable area. And associated with that, so this was something that had occurred back in the 1930s, 1940s. So essentially looked at landscape images and associated that with some changes that occurred down here in this part of the system, in part in the introduction of salt water into these marshes from piercing what was a berm that occurs along the southern portion of Everglades National Park. And so these are just a couple of the images that have been collected out in the park, illustrating this loss of sawgrass plant communities and low productivity associated with increasing saltwater intrusion. So the Everglades is not only compromised by the fact that we have diverted quite a lot of the fresh water that used to flow through that system, but now we are facing an increasing influence of sea level rise. And so we had a nice presentation from Tampa Bay region, starting to develop some of these sea level rise projections for vulnerability assessments and planning in that area. And in South Florida, our 4-county compact has also developed these sort of unified sea level rise projections. And up here is just what they're using for the planning horizon for infrastructure, new infrastructure coming into that area and adaptation projects. And then some more recent information has come out that's indicated an uptick in the rate of sea level rise over the last decade or more. So the average or the global rate around 2.5 millimeters per year, and with this uptick that's actually in part been identified for southeastern Florida, up to 9 millimeters to 1 centimeter over the last 15 years or so. It's still up for debate as to how exactly this is happening, but part of it has been attributed to the slowing down of the Gulf Stream with changes in oceanic circulation patterns. So no time like the present to understand what's going on in our system associated with sea level rise and saltwater intrusion. And I just grabbed a couple of the images that came from the USGS, some of their gauges in the southern Everglades, and these are showing the passage of Irma. So oh, the arrows in there? No. So the arrows didn't quite show up, but here essentially, so right around in here is where we observed a 1 foot increase in surge height associated with the passage of Irma. And then down here where there's in a site called Alligator Creek, it was about a 6 foot passage, 6 foot increase in storm surge associated with that event. So the storm surge attenuation capacity over a pretty narrow region of those wetlands is pretty immense. But not only with that storm surge attenuation, we also see increased salinity associated with these pulsed events in the system. And so one of the large sources of uncertainty, so this was something that was produced by the U.S. Army Corps of Engineers and reproduced in the Committee on Independent Scientific Review of the Everglades Restoration Program, their report. And essentially it shows we have no idea what sea level rise is, how it's going to affect our coastal wetlands. Over here, this sort of grayish area here is showing vegetated wetlands. And this is with 2 feet of sea level rise plus the introduction of, plus a completed restoration program. On the right here, this is an image of 2 feet of sea level rise without restoration. So no redirection of a lot of that freshwater flow that's intended with the CERT program, essentially showing that all the peat is gone. So there's a lot of uncertainty in terms of what we anticipate this to look like, as well as this. And this is a big a management need and something that the South Florida Water Management District had identified as something that they needed more help with in terms of the scientific support. So this is just a quick schematic that's one of the infographics that's come out of the work that we've been doing. This was produced by a communications firm and the Everglades Foundation. But essentially what we want to be able to understand is how is sea level rise, saltwater intrusion, salinity interacting with our formerly freshwater peat wetlands, so that we can get a better handle on how those wetlands are going to change in the future associated with increasing influence of saltwater intrusion, and what sort of freshwater delivery, what sort of freshwater conditions would those wetlands need if we were to try to maintain them in their persistent or healthy nature, so that we could continue to have persistent vegetated wetlands in the Everglades and certain areas, and continue to confer those ecosystem services that we have come to depend on. So this is just a quick schematic illustrating the process of what we call peat collapse. And so what we're trying to do is to develop mechanistic research that allows us to connect the process of peat collapse to what we project to see in the Everglades, or what we may project to see. So to address these research questions, we pulled together a team to focus work that both had a laboratory mesocosm approach where we could develop very controlled conditions so that we could test the influence of salinity and inundation on these sawgrass peat monoliths, or large clumps of peat, if you will, at a facility in Key Largo that's also co-managed by Everglades National Park. And then also coupling that with field experiments. So set up large chambers and dose these chambers with aliquots of salt that allow us to simulate the pulse of salinity associated with storm surge events. So this being a more controlled experiment where we can apply continuous levels of salinity to understand the response of these vegetated wetlands to salinity increases, and then a field experiment that introduces a bit more variability and less control in terms of how we set up the experiment, but allows us to relate these controlled results to those that we find in the field and ultimately scale those to a level that will help us to understand landscape change. So this is a shot of one of our field sites. We call this the Brackish site. And so we tried to identify a place in the park where this process that we were observing, this process of peat collapse already occurring. And we actually brought one of the Everglades National Park chief scientists out with us, and she said, "What's going on in my park? I've never seen this before." So just in getting the permit for the project, the resource managers were already excited that we were starting to do this work out there. And this is just showing some of what it looks like on the ground. We have the loss of these plants. They start senescing, and then that opens that. Because those plants aren't producing that root material that's going into the ground, the soil material starts to fall apart, and you get this open ponding associated with increased salinity. So these are the questions that we're testing with this work. So I'll just show a little bit of the results. So all of this work comes from our PhD students that are just getting ready to finish up this year. So we can expect to see lots of resulting from this. But one of we took a lot of measurements to try to understand the carbon balance. With the carbon balance, we could relate to how these wetlands will perform at a larger scale. So part of that carbon balance is understanding the biomass, the productivity of the plants. And this is a graph showing the change in above ground biomass of these sawgrass plants. So these are sawgrass plants that have been known to have some level of tolerance to salinity, but there's no literature at all to let us know what that salinity tolerance is, which is very key to the production of their soils, because all the material that those plants are producing is basically what that soil is. It's all dead organic matter. So if these plants aren't producing roots, then they're not producing the soils that allows those wetlands to persist. So these are showing, this is biomass of plants that are in sort of ambient salinity, and this is elevated salinity. So we're seeing a decrease in the ability of those plants to maintain their persistent levels of biomass with increasing salinity. And this plot here is showing annual net ecosystem production. So this is exchange of carbon dioxide with the atmosphere. And here with ambient salinity, so no change in the salinity from the conditions with which we pulled them out of the wetlands, those plants are continuing to sequester carbon and put it into the ground. Whereas these plants here, exposed to higher levels of salinity, actually twice ambient, are showing that they are a source of CO2 to the atmosphere and therefore not sequestering carbon and putting it into the ground. So this is from the field experiments, and what you see here in the blue line is basically water level, and the purple line is the ambient chambers that are in the field, and the green ones are those where we added salinity. So we add salinity once a month and ramp up the pore water, the soil pore water, to twice ambient. So what you see is that when the water level recedes, that marsh becomes a source of carbon to the atmosphere, so it's no longer putting carbon below ground. And what we see over time is that with increased salinity, when the water level recedes below the soil surface, it becomes an even greater source of carbon dioxide to the atmosphere. So salinity is basically ramping up that effect of lowering the water table, or the water table being lowered. And so we put all of this information together to develop different approaches to understand the carbon balance of those wetlands. And so what we're seeing is that, so this, for example, is ambient salinity with plants that are exposed well, these are plants in ambient salinity conditions, and these are plants in elevated salinity conditions. And basically in ambient salinity, they continue to sequester that carbon, and we have an idea of what that is, and they're not sequestering much carbon associated with that salinity. But you might notice a little bit of irreconcilable difference between a couple of our estimates and what Ben, the student, had called unaccounted for carbon. And so the next phase of this is relating this information to actual change in soil elevation. So we expect that that residual term is associated with the carbon that's being sequestered in the soils. And so we're going to couple this work with an existing sediment elevation table network, so we can ultimately scale this to answer some of the questions the large-scale questions that we hope to in the future. So I think I'm probably out of time, but just to synthesize very quickly, the work is helped us to understand what the threshold for salinity, for the threshold for plant production of these really important sawgrass plants. So now we know that they can only tolerate certain levels of salinity, and we know what that is. We know that that increased freshwater delivery will help reduce salinity exposure, but some other information is illustrating that freshwater delivery at its current level is not sort of freshening that pore water that the plants are responding to. So there's a lot more work that needs to be done there in terms of getting more water into the system to change that current situation. Thank you very much.